Okay, good afternoon, 61C. Good afternoon. Wow, you guys are worn out. Okay, let's get started. So, today we're going to talk about really one of the great ideas in computer architecture, caches. If it wasn't for caches, we would not have any usable computers these days. They really are one of the key ingredients of modern systems. So getting back to our stack of all the different pieces, where we are today is how do you get high performance, and in particular looking at the cache memory system, basically the memory system inside the machines. So let's go back to this diagram we showed you a few times about the main components of a computer. You have the processor itself, you have the memory system, you have input and output. And today we're going to focus on this processor to memory interface, how the processor reads and writes data out of that memory. Now, one thing that you might not be aware of is how slow memory is these days compared to a processor. And this gap has grown over time. So this data is plotting the relative improvement in processor speed, how fast an instruction can be executed, versus the improvement in memory access time, which is the number of nanoseconds it takes to access a word in memory. So how much are those improved? And so this x-axis along here is years, so just time. And the y-axis is performance, so the speed at which you can do a single access or a single instruction. And notice that's a log plot on the y-axis, right? So when people talk about Moore's law, it's this exponential, things have been getting better at this rate. And so microprocessor performance, at least during its heyday over the last few decades, improving around 60% per year. So every year the processors were 60% faster than the previous year, 1.6 times faster. Memory, on the other hand, was only improving about 7%, so 1.07 times faster than the previous year. And this has been going on for some time. And the difference between two exponentials gets to be pretty big over time. And so a 1980 era microprocessor, that would probably execute an instruction roughly the same amount of time it took to fetch a word from DRAM. Fast forward to 2015, so a modern microprocessor can execute about 1,000 instructions in the time it takes to get one word of data from memory. And that is a huge gap, right? It's a long time to wait for memory. And so if this was the end of the story, we'd have very, very slow computers. They wouldn't be much faster than they were back in the 1980s. So this incredible gap is one of the chief challenges in computer architecture, and architects spend a lot of time worrying about the memory system. Now, fortunately, there's one big saving grace in the way applications run that architects take advantage of in building something we call a memory hierarchy, right? And so the big idea here is when the processor goes to memory, instead of having all of memory just as one monolithic, great big lump of memory that takes a long time to access, you instead build a hierarchy. We have multiple levels of memory. And the idea here is that your big bulk memory is in the outer levels of this hierarchy, sort of at the bottom of this pyramid. But inside that, you have these smaller levels. And the idea is that as you get further away from the processor, and that you can build a bigger memory system. Just pure physics tells you that. You can travel further, you can access a bigger memory, but that's going to be slower. If you build a smaller memory, you can be closer to the processor, and you can make it faster. So basically, the further away you are from the processor in terms of time, the bigger the memory can be. The closer in you are, the faster it can be. And we're going to take advantage of that by having multiple levels where the inner levels are small but very fast, and the outer levels are big, but as a result, extremely slow. Okay, and there's an analogy we use to explain this idea of caching from using a library, right? So you go to the library and you have a homework, and you have to go write a report on the works of Salinger, right? So you go to the library, you go find a reserved book, you place that on your desk in the library. You start reading through that a bit, realize there's some other books you should go get. So you go get those few other books, put them on your table. So after a while, you have, some number of books on your desk, and after a while, if you want to get a new one, you have to put one of the old ones back. There's only so much space on your desk. And you're relying on the fact that even though the Berkeley Library has a huge number of volumes, only a few of them are about the thing you're actually interested in right now. Right? So right now I'm doing this report in Salinger. I just need to get the books related to that on my desk, and I can work on that small thing. So instead of having to have the whole library on my desk, I just need to have a few books on my desk. Right? So you only need a fraction of all of the storage in the library to complete your current task, which is writing this report. Now, fortunately, when programs are run on computers, they have a similar property. And this is really fortunate, because if this wasn't true, we couldn't build computers that would be effective. So what this graph is showing you, this is some very old data from 1970, a paper in 1971, but the plot is nice and it still shows the main ideas. So what this plot is showing you, it's along the x-axis is time. So just as the program's running, we're plotting something. And what we're plotting on the y-axis is memory address. So these are different regions of memory, and every single dot on here represents a memory access by the processor. So every dot says at this point in time, this processor accesses memory location. Okay, so it's just a scatter plot that's maintained over time. What would this look like if program accesses were random to memory? What would you expect to see? Noise. Just look like noise. Do you remember TVs, antennas, those things before the internet? And if you weren't tuned into a channel, you just get fuzzy noise on the TV. That's what you'd expect to see, right? Just random black and white. But that's not what you see, right? What you see here is very definite patterns. And those patterns represent properties of the program, how they're accessing memory. Okay, so it's not just random. If it was random, there's not a lot we could do about it, but we can see there's some structure here. And that structure is what we're going to exploit in building the memory hierarchy, right? So the thing to notice, all the white space is regions of memory you're not accessing, right? The black dots are where the program's actually touching those locations. The white is where you're not making an access, right? And notice it changes over time. You're working here, then you're working here. But the white space is kind of as an opportunity. I don't need to have those memory locations close by. What are the ones I'm working on? Just like in the library, you only need the books you need, not all the books in the library. Yep?
Can you just explain one more time why couldn't we just have big memory why couldn't we have a lot of memory really close to us and then a lot of memory farther?
So the question is, why can't we just have a lot of memory close to us? Well, we live in a 3D world, and every piece of memory has a finite size, occupies a finite volume, and the more you want, the further away some of it's going to be. They can't all be next to you, right? We only have 3 dimensions, so physics just constrains ultimately how closely we can pack memory cells. And so it's just inherent that big memories are slow memories, because most of the memory access time is taken in getting the signal to the bit and back again. And so if you want a big memory, you can have a big memory, but it's going to be voluminous, and as a result, signals take time to propagate across that big memory. You might think, well, these things are pretty small. My laptops are tiny. The memory's not that big. But in terms of speed of light and how fast the processor clocked, remember we're running at sub-nanosecond clock rates, periods. 3 gigahertz, 0.3 nanoseconds. Light goes about this far. And light travels even slower than that in electrical. Signals travel even slower than that in wires. And so, you may think, well, this is tiny, but relative to the speeds we're running at, it's kind of quite big. There's also time spent to buffer the signal up so we can drive that huge distance. Electrically, this is a huge distance. But that's the real reason, just physics. It's fundamental physics. There's not a lot we can do about it. So the big idea we're going to exploit in the memory systems is this notion of locality. Question?
I have a question about the graph on the previous slide.
Sure.
It seems to be like a whole lot of horizontal lines. Is that like a bad scan, or is there some reason that there would be like an even spacing of accesses to memory at specific locations?
You're saying that these gaps here seem about even. Yep, good observation. I'm not sure what's happening in this particular memory trace, why there is such a even spacing. It might be there's some particular variables that have been accessed, some pieces of a matrix or something, possibly, have been laid out in that way. And maybe This is stepping down the rows of a matrix in some way. I don't know. So the big idea we're going to exploit is locality, right? And there's two forms of locality. One is temporal locality, locality in time. And the analogy here is, you read one piece of the book, you're writing something down, you have to go back to that piece of the book, you forgot what you just read, you go back and read it again. So if you've read a book recently, it's pretty likely you're going to read that piece of that book again. The same in the computer system. If you've accessed a given memory location, it's highly likely you'll access that same location. Or rather, it's much more likely you'll access a location you've recently touched than any other location in the system, right? This is just the property of programs. Spatial locality says if I've accessed one location, it's much more likely I'll access a nearby location versus some other location, right? So, if you go doing a report in Salinger, you're probably going to pick up a few books in the same portion of the library, right? Rather than random books scattered across the whole library. They pack them all together, so you're going to go to the same shelf and find several books you want there. And the same thing happens in programs touching memory, that once you access one memory location, it's highly likely you'll access some locations nearby. And by highly likely, I mean much more likely than in any other random location in the system, right? So these two properties are things these are empirical observations we've made over time by looking at how programs are run. So running programs tend to do this. People don't tend to write programs that access memory randomly. Just not what programs do. And so these two properties are things we're going to exploit in building the memory system. So temporal locality is if you access one location, it's highly likely you'll access the same location pretty soon. Spatial locality is you access one location, it's highly likely you'll access something nearby pretty soon. So those are two forms of locality. And these are really forms of predictability. The program's doing something kind of predictable. We can guess what it's going to do next and take advantage of that in building our memory hierarchy. So let's go back to this plot and let's look for temporal locality and spatial locality. So what would you expect temporal locality to look like on this plot? You access the same location, you access it again in the future. What would that look like on this plot? There's a horizontal line, right? It's a horizontal line. So you access one location here, I'm going to access the same again. Look here, you see there's lots of horizontal lines. So this is some location that's repeatedly being accessed, and that's an example of temporal locality. How about spatial locality? What would that look like? Right, look at these hashed regions. I can see people doing this, going up and down, right? So if I access something here in this neighborhood, I'm going to access something nearby. Notice here, it's more likely to access something here than something over here, right, far away.
Is the reason why there aren't jobs in between really because, like, if those are memory addresses, is it because you can't access, like, 32.5?
Well, notice you do over here, right?
So then what? These numbers represent exactly, because it says memory addresses, but
So I have a few more examples that may give you some hints about what's going on. I'll go through that. So just bear with that for just another slide or two. So temporal locality is these horizontal lines, and spatial locality is kind of these black regions where neighboring things are being accessed. And notice where you're touching moves over time. So over time, as the program runs, it's dynamic. Like some areas become hot, some areas become cold over time. So here there's a hot area here, then I didn't access it later, then here this became hot, this region over here. So the structure we're going to build is going to have to respond to this dynamic reference stream coming from the processor. So as the program is running, we want to change the locations that we bring into our inner levels of the memory hierarchy, right? We have to adapt to it dynamically. Okay, so the principle is programs access small portions of address space at any point in time. Let's go talk about what kind of program structures. What is it in programs that leads to this, right? We've observed this. If we just watch the programs running, we see this behavior. But let's do a bit of analysis. What is happening inside the program that makes it exhibit temporal and spatial locality? Let's break it down. How about instruction accesses? Right, so remember the program, the processor is accessing memory both to do instruction fetches and to do data loads and stores. What is it, if we focus on instruction fetches for now, what are the properties of programs that give instruction fetches temporal and spatial locality? Let's try an easier one first, spatial locality. Where do you get spatial locality in instruction fetches? Yep. Right, so the normal way program execute just sequentially. I execute an instruction at the PC, then I move to the PC plus 4, and I'll keep going unless there's a taken branch or a jump. Right, so just naturally straight line code has spatial locality, right? Just falls out of how you arrange the code in memory. How about temporal locality in instruction accesses? Where does that come about in the way you build programs? Yep. Right, so you have a loop. So I execute this set of instructions, I branch back around, and I execute the same set again. So loops are a great example of how an instruction stream you're going to find temporal locality. Okay, so you can see now that it's actually a property of how all programs work. It's not just fluke that the ones we looked at had this property. It's kind of intrinsic to how programs are written and developed that these properties are there. How about data accesses? So let's think a minute about where will you see temporal locality in data accesses? What's an example of program structure that would lead to this? Yep. Yeah, so you declare some variables in your program, and you're reading and writing the same variables, and those are stored at some address. And if it's a variable inside an inner loop of your program, you're going to be repeatedly reading and writing the same location in memory, right? So touching the same variable over and over again. How about spatial locality in data accesses? Yep. Right, so a great example is an array in memory. You have an array stored, and you're going to step through it, like index element 0, element 1, element 2, element 3. They'll be stored next to each other in memory, so it's quite common to step through an array. And stepping through an array will result in spatial locality that you'll see in the address stream coming out. So now you should hopefully be seeing that. It's not just a fluke. All programs kind of have structures that lead to these properties. So let's just kind of illustrate some more of this. So instruction fetches, we already talked about this. They kind of look like this. So you start up, if addresses go up the page, this is stepping sequentially through some routine, and this is just looping around, right, and stepping off the end of the loop. So you do some number of loop iterations and jump off. So these are the kinds of patterns you'd expect to see in code. Now remember, we have several regions of data storage in our machine, on the MIPS processor in particular, and the stack is used to hold your local variables when you make a function call inside a function. And so what you expect to find is, you're placing arguments on the stack, you'll make some memory requests, you may access a local variable held on the stack while the subroutine's running, then you may restore, like this is saving the save registers, restoring the save registers. So you're going to get these kind of structures, these patterns showing up just because of the calling convention for data accesses on the stack, right? So that kind of structure in the program is reflected in the structure in the memory references made. Finally, we talked already about data accesses, so you kind of see these patterns where if you're accessing a vector and stepping through the elements, it looks like this. Or if you have some, scalar variable, you just access the same location repeatedly, okay? So now this kind of helps you explain, maybe go back to the scatter plot. You start to see, like, this is some kind of vector access here, some array. Notice you're accessing these at different rates, depending on the loop. I know these might be code regions, and, these might be equally, there may be some matrix column where you're skipping every 100th element or something that might explain this pattern here, okay? And this looks like maybe some code loop executing here. Maybe this loop is the instruction fetch that's accessing this vector, right? So you see these patterns in the memory reference patterns. So what we're going to try and do as architects is exploit these properties we found in the programs, and what we want to do is add a cache, and the idea of a cache is to build a programmer-invisible hardware mechanism. Programmers don't know it's there, and we want to give the illusion of having a huge memory that runs at the fastest speed possible, and we want this to work even if the programmer has no idea what a cache is. All of you who've been writing programs merely without any idea there was a cache in there, right? It works, right? You don't know it's there. However, if you're really performance-oriented, you'll see that the restructuring your code if you know there's a cache there, restructuring your code can give you huge speed-ups. And you'll be exploring that in Project 3. And actually a competition to see who can write the fastest code to rework things to work well with a memory hierarchy, right? But most of the time, the idea is programmers shouldn't know this is there. It should just speed things up without the programmer being aware of it. So it's programmer invisible hardware mechanism. Let's see how this might work. So let's first of all do this without a cache, just go into memory. So we have a load word instruction. So we load from address given in T1, 0 offset, into a register T0. So say T1 contains address 1022, memory contains 99. Sequence is the processor is going to issue this address to the memory. It'll take some time for the memory to respond, depending on how big the memory is, right? So the bigger the memory, the slower. It's going to read the word at that address, send that to the processor, and the processor puts that into the register T0. So this is just a conventional thing we've looked at so far, just directly accessing the memory and putting the value back into the register. So now let's try and speed this up by adding a cache to the computer. So this is our picture from before. And so the processor is putting the address out to the memory, waiting for the memory to respond, and then sometime later the read data is going to come back into the processor. So the bigger that memory, the slower that's going to be. Where the cache goes is right here. So what we're going to do with the cache is intercept all the requests being made to memory. And what we're going to try and do is satisfy as many of those requests from the cache as possible so you don't have to go all the way out to the big memory, right? So, and the trick is going to be holding on to locations you've touched in the cache in case you need them again, right? So this is where the cache lives. You can think about it just as intercepting all those requests going to memory. So actually the processor itself, the hardware there, doesn't even need to know there's a cache present. It just sees the memory coming back quicker than it did before when there's what we call a cache hit. All right, so that's where the cache lives. So now the process will be, if I do this load word instruction in the hardware, with a cache, the processor issues that address, but now it's intercepted by the cache. The cache looks at the address the processor is trying to access and does a search in the cache to see, do I have that address? If I have that address, I could return the data immediately to the processor without waiting for the memory to respond, right? So we call that a cache hit. When you hit in the cache, the data is there, right? However, if the cache sees that address and says, you know what, I don't have this location, then there's no choice but to go out to the big memory, wait for it to respond, and return that data to the cache. But the one thing you'll do now is, well, if the processor wanted that data this time, by the principle of temporal locality, it's highly likely it's going to want that data again soon. So what I'll do is, as well as returning it to the processor to satisfy the load request, I'm also going to keep a copy in the cache. So any request that misses in the cache, I go out to memory, bring it in, give it to the processor, but also keep a copy in the cache in case the processor asks for it again. Now, the thing is, the cache is finite size. It's small. Remember, the whole point about it's small and fast. But because it's small, whenever you bring something in, you're going to have to kick something out. So you have to decide on what are the things I've got to hold on to, and I'll kick something else out to make room for the new item that came in, right? So you read the memory word, send it to the cache, replace the some entry in the cache with this new word, and then send it on to the processor. So now the next time the processor comes to that same address, it will be in the cache, and you get a cache hit again, right? Okay, so, all right, let's take a little break. Minutes trivia. So let's talk about midterm 1 results. They came out last week. So Project 2.1 is due on Sunday, and please use the pinned Piazza threads before posting questions on Piazza. It's very hard to keep up with people randomly asking the same questions over and over again, and they're pinned by section. And we're going to penalize those who ask the same question again, because if it's clear you didn't search, we're going to keep track of that in your EPA points, right? So do the search first, right? We have a cache of all the questions there in the threads, right? Another thing we're starting, due to popular demand, the readers have agreed to help run guerrilla sections starting this weekend. So these are sections to cover the material in the lectures and possible exam kind of problems, work through those. So it's not a place to ask questions about the project. It's just about more time on the lecture material. So go to Piazza. There's a poll there for when you would like those to be. There's a few time slots, so go vote for when you would like those to be. And so the readers are volunteering to do this to help you guys learn the material. I realize we're getting through a lot of concepts very fast in 61C. This is some way to help you get some extra time to go over them. However, you shouldn't feel bad because this is the midterm score distribution, and you guys are doing pretty well. Like, people say it's going fast, but judging by the exam, you guys are learning the material. So, over half of you got more than 2/3 correct on the midterms. That's a pretty healthy distribution. So, somebody got full marks. So, one person. So, we feel that's a perfect exam, right? Stretch the range. All right. So, so you guys are doing great. Okay, so the growth section should help. All right, so let's stop and take a 2-minute break. I have time for that. What values are held in this memory versus... Those are my memory address. Which memory address am I touching? Those memory addresses you can actually close to me.
Really quick question. I on accident grabbed my roommate's clicker. So I just wanted to, it's more administrative.
Just mail soccer.
Okay, should I click with this then?
Yeah, just click with that and mail the ID.
Okay, awesome. Thank you.
Okay, let's start up again. So, I was going to tell you this. One thing in the news, this was a cute little thing I saw pop up. So a little while ago, some researchers at CMU and Intel found out that memory chips, like DRAM chips we use in laptops and servers, are susceptible. If you work very hard, you can bang away on one piece of the memory and cause neighboring bits to change, which they shouldn't do. Like, this is an error in the way chips are made. That the chips that you buy are susceptible to this. They weren't quite designed to tolerate extremely high writes to a given area of memory. So if you actually wrote to a location repeatedly, you could flip neighboring locations. And recently, Google engineers figured out how to use this to gain root access on a machine. So they could figure out just exactly which bits you were in memory and hit a neighboring piece of memory and flip a bit that would give you access to a machine. So the bad news is that almost all laptops are susceptible to this attack. If you have the servers and desktops that have ECC memory with error correction, they're much less. It's much harder to get the bits to flip in a way that the ECC doesn't catch, right? But this is an example of main memory being used as a attack vector. So, anyway, that's a cute thing in the news. All right, cache tags. All right, how are we going to? Now we have to sort of get the general idea of how a cache is. So, a lot of what we're going to do over the next couple lectures is go over all the different ways caches are built. And we'll just give you an introduction to this because I think there's probably been like literally 2,000 or 3,000 or 4,000 papers written on how to build caches, and there's probably a few thousand patents on different aspects of cache design. Because this is so important to computer performance, there's many, 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 many ways of building it. And we'll just focus on the key sort of fundamental cache designs. And then if you get involved in computer architecture, you'll spend a lot of time playing with caches of various kinds. They're a very important concept. So we'll just do the basics here. How do you build a cache? Well, one thing, the cache is intercepting these requests, and the processor is asking for a memory address. So you need some way, the hardware in the cache needs some way of telling if it has a copy of that location or not. And the way we do this is, in addition to the data storage in the cache, which holds a copy of the data, each of those locations has another associated piece of memory next to it that holds the address. So that's called the tag. So every data location in the cache has a tag, and the tag says which address it corresponds to. Now, remember, in main memory, you don't need a tag because you can just tell by location. Location 47, that is address 47. But the cache is much smaller than all of main memory, but it can hold anything from anywhere in main memory. And so the cache may have, say, 8 locations, but any of those 8 locations may hold any address from anywhere in memory. So you need a separate tag on each of those data items that says which address it came from, right? So that's being shown here. These are addresses, and this is data. So this cache line here says this data word 99 is from address 1022. And so now when the processor makes a request to the memory system and the cache intercepts it, it's going to take that address and compare it against all the tags in the cache to see if it has a match, right? So you're storing the address as well as the data, and then you're dynamically, as the access is happening, comparing the address to all those tags to see if there's a match. And the cache over time will build up a collection of data. Notice these addresses are from anywhere in memory, or just located in this cache. So there's quite a few design parameters for cache. And let's look at a very simple design for now. So this is a cache that has 16 bytes total of capacity. Question?
How come the cache is faster? You have to search through it. It needs access, like, index normal memory. You need to access the address. How come it's faster?
Okay, so it's a good question is how come the cache is faster if you have to do all the searching? We'll get through faster ways of doing the searching. So it actually looks a lot more like accessing regular memory. So for now, we're just building up a simple model of the cache, and through the rest of today, we'll make it a bit more realistic, and you'll see how we can make it fast. So here's a basic idea of a cache. Here's the processor, here's the memory, here's the cache in the middle. So we have addresses coming out of the processor, 32-bit addresses and 32 bits of data. So each block here, each piece of data in the cache, in this case, is 4 bytes of data. So when you make a request, you check the address. If you get a match, you respond with the data in the block. So things you can do, you can get a cache hit. You make a request from the processor. It's in the cache. You return the data. You can get a cache miss. It's not present in the cache, in which case I have to do the third thing, which is refill from memory. Go get the data from main memory, write it into the cache, and then return it to the processor. So in this simple case, I'm just going to compare this address against all these tags. And the thing to know is if it's only a few locations like this, it will still be pretty fast. You're talking about 4 words of memory as opposed to billions of words of memory. So, size is one of the key things here. So if it's small, the signals can propagate. Logic takes a little bit of time, but this is really tiny compared to all of main memory. So this can still be fast. But you're comparing this address against all those tags. So the simple design, you've got to compare all 4 tags against the address. So like I mentioned, one of the problems you have to solve is when you do get a miss, I need to bring some new data in, and I want to remember it because of temporal locality, but that also means if somebody comes in, somebody has to leave, right? You need to pick a victim line that gets evicted from the cache when a new request comes in. And a big question is, which one should I evict, right? The obvious answer is not one I need anymore, right? But it's a little hard to figure that out. We'll get to that a bit later. Let's assume you have some way of picking the victim, and then we'll override it, right? So say request location 511. Nothing matches here right now. There's a miss. So I'll pick this guy to victimize. gets kicked out and replaced by 511 with data there, right? So that's cache replacement, the process of kicking somebody out, replacement. So now we start getting into some of the design simplifications. So that cache before we set at a 4-byte block to match the word size. And to make the cache design simpler, an obvious thing to do is to require that those blocks are 4-byte aligned in memory, right? They can't just start in any location. They could only start on 4-byte boundaries. So the convenient thing here is if we make the blocks aligned, then we know that their start address always has the last 2 bits 0, right? The 4-byte align, the last 2 bits of the address must be 0. And so how are we going to take advantage of that? If we always know the last 2 bits of the address is 0, where can we save hardware? Yep. Say again? Right, so the tags for each entry need 2 less bits, because you always know the last 2 bits of the address is 0, so you can shrink the tag by 2 bits, okay? Also, when you're doing the comparison, you need to compare 2 fewer bits, right? So you're only comparing 30 bits, not 32 bits. You save a bit of hardware there. So as we said, the tag could be narrower. So we can continue this thought a little bit more and say, well, that worked great for 4-byte blocks. Why don't we make the blocks bigger? All right, so let's have 8-byte blocks at the cache. So now we have 32 bytes of capacity. We still have 4 tags, but now we've said each block is 8 bytes from memory, but they have to be 8-byte aligned. So we'll always bring them in an 8-byte boundary. And in this case, the tags only have even-numbered words, and so we can save 3 bits from the tags, right? So now 8-byte aligned, we only need 3 bits less in the tags, 3 bits less to compare. And now a word can be read or written from either half of this, and so we need to look at 1 bit of the address to decide which of the 2 halves of the 8-byte line am I actually requesting, right? But you don't worry about that going out to memory. You just do the tag check on the high bits, the high 29 bits. The next bit will tell you which of the 2 words it is, right, out of that line in the cache. Okay, so we started to simplify the cache hardware, right? And so you can get a hit for either word in the block. Okay, so let's start cutting down this tag comparison cost. So design so far what we call fully associative. And by that, it means every tag is checked on every access. That's what a fully associative cache is. Every tag is checked on every access. And that means that any location in memory could live in any location in the cache, because I'm going to search all locations in the cache for any address that comes in. Now, the comparators can get to be kind of expensive, both in terms of area and power, to do all those comparisons at once. So one optimization is to say, well, instead of viewing it as one cache, I'm going to split the cache into 2 sets, what we call sets. And each set will cache half of memory. So based on 1 bit of the memory address, I can tell whether it's in the top cache or the bottom cache. The top set and the bottom set. 2 sets. Then only to search half of the cache to find a memory address, right? So 1 address bit selects the set in this case. So that's what I'm showing here. We sort of divided the cache this way into set 0 and set 1. So based on 1 bit of the address coming out of the cache, out of the processor, I only need to check against the tags in that half of the cache, right? The correct set. Yep, question?
Would it always get, so why couldn't you have like 8 sets?
And often you do. So we're sort of building up to it, right? So this is getting you an idea, right? So now I'm using 1 bit of the address to select which portion of the cache to look in. And we call these sets because within a set, these locations are equivalent. So you can have any location in memory that maps to that set can live in any way in the set is what we call each of the locations in a set a way. We'll get to that in a minute. So in general, expanding this to the general case, you can take the address that comes out of the CPU and break it into 3 fields, right? Tag, index, and offset. So the easiest to understand is the offset at the low order bits, the least significant bits. So the offset is just where in the cache block are you. So if you have a 4-byte block, it'll be 2 bits. to say which byte you're interested in. If it's an 8-byte block, you'll have 3 bits, which say which byte you're interested in. And you can make it a 16-byte, a 64-byte, 128-byte long line. So each cache line is this long, and this offset just tells you where within the cache line I'm interested, right? That's the easiest piece of the story. The next few bits you use as the set index. So the set index tells you which partition of the cache do you need to search in, which set of the cache am I looking in right now, right? And so that's this portion of the address, and the final portion is the actual tag bits that you need to compare. Okay, now the important thing to get across here, the bits that I use for block offset and set index don't have to be in the tag because they're implicit in, either it's a piece of the line or it's whichever set I'm in. Like all the entries in set 0 have the same 0 bits in their address here, so there's no reason to store those bits in the tag. You already know by looking in that set that those bits are 0. You only need to store the high bits, the tag bits, to check whether you have a match or not in the cache. Okay, so we're just working through this. So number of sets, take the log 2 of those, that gives you the size of the index. And the size of the tag is just the total address minus the index minus the number of bytes, the log of the number of bytes in a block. So let's take this as far as we can. It's always good to hear Daniel. Well, if we go back to this case, so this is where the sets are. So the offset tells you where within this block. So if this was just 4 bytes, you just need 2 bits to select the byte within that cache block, right? That's the offset portion. Then the set index is 1 bit in this case that tells you whether it's set 0 or set 1. I need to look in. And the high order bits are the tag that you actually compare against the stored tags. And the point here is that any bits I use for the set index, I don't need to store those in the tag because it's implicit in which set I'm in, what those bits should be, right? So if the bit is 0, I'm going to be searching in this set. I don't need to store a 0 in the tag. If the bit is 1, I'll search this set, and there's no reason to store a 1 in the tag. So that's why as you increase the number of set index bits, you decrease the number of tag bits you need. So the obvious question is, well, that's great. How about we get rid of, what's the most? How can I get rid of as many comparators as possible? Well, one answer is you make the set index be large enough so every line is in its own set. So every entry in the cache is in its own set. And then there's only one tag you have to check, right? So that's called a direct map design. And actually, the very first caches were built this way. So direct map design, I'll go over this. There's the index bits. 2 to the number of index bits gives you the number of lines in the cache. So directly from the index, you can tell which line you need to look at, and there's just one tag there you need to compare. And that's how it gets to be about as fast as accessing a small memory, right, when you build a direct map cache. So we just build this up with a very simple example. We're just going to have, to make things tractable, we do a 6-bit memory address. And so the 6-bit address will have the offset field be 2 bits, a byte within a word. So the block size is 4 bytes. So these 2 bits just represent which byte within a word. The next 2 bits will give the index, which set to touch. And the top 2 bits will be the tag. Okay. Before we get into the cache design, one more detail. When you start up, you power up a processor, the cache doesn't really have any valid data in. It's just, you just power it up and it just has garbage in, random data. And so one of the features you need in a cache is a valid bit that says, in addition to checking the tag, I have to also check the valid bit to make sure this entry has real data in versus some junk that I got from power on, right? So that you set the valid bit when you first write to that line, and then the line can stay valid because that means the address is valid. Okay, so this is just an extra detail you need in the cache. So let's go through this example. So what this is showing is this is main memory. So this cache, remember, has only got 4 entries, and we only have a 6-bit address space. We can draw all the entries in main memory here, just to give an example. So there's many entries in memory. There's just a few entries in the cache. So remember, the last 2 bits tell you which byte within the word. So we're just going to ignore those and call those XX. So these other high order bits tell you, the top 4 bits tell you which word in memory it is. And these black 2 bits, these black 2 digits are the set index, and the red 2 digits are the tag. But notice here, just the memory, they're just sequentially going up. Here's word 0, word 1, word 2, word 3, 4, and so on, down to word 15, right? You have 6-bit address space, 15 words, 64 bytes total. So a direct map cache basically says if I look at those 2 bits, the index bits, they tell me the one and only place that memory address can live in the cache. If it's in the cache, it has to be in this one location, right? So that's kind of shown here. So these 4 can live in those 4, but the next 4 just wrap around. They live in the same location. So this guy, all the entries that have the 2 black digits 00, they all map to set 00 with index 00, right? So this guy can only live there. This guy can only live there, and so on, right? So every block in main memory has exactly one place in the direct map cache it can live, one and only one place. Okay? And you can tell which one is in the cache by looking at the tag field. So tag field, if this guy's in the cache, the tag field has 00. If this guy is in the cache, the tag field will be 01. If this guy's in the cache, the tag field will be 10. If this guy's in the cache, the tag field will be 11. Okay, so the tag tells you which of those possible memory locations is in that line in the cache, but there's only one place in the cache that any memory line can be, because this is a direct map cache, right? So you cannot, you can't hold any arbitrary 4 words in the cache at the same time. Only 4 words that live in different sets can live in the cache at the same time. So now you've made this restriction on how memory locations can map to cache locations, and you did this to make the cache simpler and faster. Okay, so the other bit you have to make sure to also compare the valid bits when you're doing this. So let's work through kind of more schematically how this works out. So we go back to a bigger cache here with a full 32-bit address space. So we're just going to have 2 bits, again, 1 byte. 1 word is the block size, so there's 4 bytes here. We then use the next 10 bits as a set index. So 10 bits we read out, and we just use those to read out. This is just held in the big memory, big RAM. We're going to read out the data, but we're also going to read out the tag, and we're also going to read out the valid bit, right? So we're going to read all those things out in that one location. So notice in this cache access, we're only checking one place in the cache, right? We read out 20 bits of tag, which corresponds to the high bits of the address. We compare those against the high bits of the address, right, using a comparator. Is it equal? The final thing we have to check is it valid? So we have to also look at this valid bit and make sure it's equal and it's valid. In that case, you can say it's a hit, right? That memory access from the processor interrogated the cache. It found that the cache at that location actually had a matching data value, and there was a hit. Yeah, question? Right, that's a good question. We'll get to it towards the end of today's lecture, but yes, if you write to the cache, the straightforward answer, you update the cache as well as memory. So you definitely want to make sure writes are visible after you've done them. So remember, one important thing about the cache, it's meant to be programmer invisible. The programmer is not supposed to know this is going on. It's supposed to look just the same as if you ran the program without the cache, just faster. Okay. So in this case, you get a cache hit. And now you can, it's safe to take this data and return that to the processor instead of the data from main memory, right? So notice how this works. You take a few bits of the address coming from the processor, you use that to index into the cache memories, holding the tag and the data. You read those out. You then compare the high bits of the processor address with the tag bits to see if there's a match, as well as the valid bit. And only then you send the data back to the processor saying you got a cache hit.
How do you, or I guess, yeah, how does it know how many bits to take for each section? That just
Yeah, the question is, how do you know how many bits to take? Well, that's a piece of the hardware design. You design this in, and it doesn't change. It's just fixed property of your particular machine that these many bits are used to index the cache. The cache is a fixed size, so at design time, you know how big it's going to be, and you decide on the organization, and you just basically hardwire. It rips out these bits and uses those to address this memory, and rips out these bits and uses those to do the comparison. It's just hardwired at design time. Okay. So what kind of locality does this cache take advantage of? Sorry? Temporal locality, right? So if you hit the same word repeatedly, it's going to be in this cache, and you won't have to go to main memory. Let's do a little more complex example, a multi-word block cache. So here, every line in the cache, so we use the term line and block kind of interchangeably to mean one entry in the cache. So I'd like to call this a line. Block is very overloaded in caches. We talk about cache blocks, cache blocking, non-blocking caches, and those all mean different things. So I prefer to use line, but I think some of the slides still have a block on them. But it just means one entry in the cache. So one entry in the cache, in this case, still has the value in the tag, but now instead of 4 bytes of data, we have 4 words, so 16 bytes of data on one cache line. So the main difference is that now there is 4 bits of byte offset to tell you where in the line you are, and that just shifts the other fields up, right? So you still have, in this case, in this case we reduced it down, I guess, to only 256 sets. So now there's 8 bits of index. So read 8 bits of index, pull out the tag. There's still 20 bits of tag. We compare that. We also still have to check if it's valid for a hit. But now notice these low bits we use to select the appropriate word from the line to send back to the processor, right? So low bits are now used to mux out the appropriate piece of that line to send back to the cache. So this is now a multi-word cache line. So what kind of locality does this take advantage of? Spatial, right? Must be the other one, right? Spatial locality. So notice that in this cache, if I make a request for this word here, and it's a word that would live there, and it's not actually present in the cache, there's a cache miss. When I go to main memory, I don't just bring in this word, I bring in all 4 words. So I go get all of them at once. It turns out it's usually a lot more efficient to move blocks of data around than single words at a time. So that first miss for one of the words will bring in 3 extra words. And the hope is that we'll use those words later. So what's interesting here, I'll effectively have brought those in before I asked for them, right? It's almost like the cache is guessing, well, you brought this word in, I'm going to bring these other ones in because I got a feeling you're probably going to touch those next. And that's the principle of spatial locality, and that's pretty common. So it's very common to have multi-word cache lines. The x86 processors using your laptop, 64 bytes is the standard cache line size in there. So they bring in 64 bytes at a time on any cache miss to any level of the cache hierarchy. Right, and that's to take advantage of this spatial locality. So there's these different organizations. So as I mentioned, a fully associative cache is one where a block can go anywhere. Yep. Yeah, so to keep the cache design simple, the blocks are always what we call naturally aligned. So when something is naturally aligned, it means it lives at a memory address that's a multiple of its size. So if it's 4 bytes wide, naturally aligned, it means it's on a 4-byte, multiple of 4-byte address. So if it's 16 bytes naturally aligned, it's always on a 16-byte boundary, multiple of 16 bytes, so that you don't have to kind of rotate and pack things around. A second reason why you don't want to do that is that you might end up having the same word in the cache in 2 different places. if you sort of access things off by one and then off by a different amount. And that would just waste space as well as cause confusion. So you only want any location in memory to appear in the cache in one place. And also you want to keep the design simple, so you just always access in naturally aligned chunks. So if it's 16 bytes, it has to be on a 16-byte boundary. You pull in that whole 16 bytes into the cache memory. Question?
How do you check if, maybe I'm more slowly confused, but like, how do you check if an element's already in the cache? Like
How do you check if the element's in the cache? Well, that's what the tag check is doing here. So it just all is done by the address of this block. So this data is a copy of what's in main memory, and that tag tells you the address of the block in main memory. You're just checking to see, do I have a matching address? If so, this is the data.
it couldn't be hidden somewhere else in some other cache?
Couldn't be hidden somewhere else. No, it's just the tag tells you what data you have, right? So going through different organizations, we went through a few this lecture, but so fully associative is one where the block can go anywhere, right? So remember the initial design we had where on any access, the cache would search every tag. That meant that any block in memory, you could put it anywhere in the cache, and the hardware would find it when you made an access. But that needs a separate comparator for every single line in a cache. Every single block, every single entry needs its own comparator to do that parallel compare. The other extreme is where you only allow the block to live in one place in the cache. That's the versions we just looked at. And that's called a direct map cache. There's only one location any memory line can live in the cache. So you only need one comparator to check the one possibility where it might be in the cache. Right? That's the simplest cache design. So most designs are actually in this middle ground, which we call n-way set associative. So one way to think about this is there's some number of sets, and within every set, it's fully associative, right? So an n-way set associative scheme, there's n places for a block within one set, and then there's some number of sets. So very common is a two-way or a four-way set associative cache, which means that there are many sets. Each set has two places a line can be in. So you can bring a line into either way within a set. The set index tells you which set to go to, but within that set there are several ways, right? That's the terminology. So as you add more ways for a fixed size cache, every time you increase the associativity, which is increase the number of ways in each set, right? So remember, the set index tells you which set to go look in. A direct map cache, there's only one way in each set. There's only one place. In a two-way associative cache, each set would have two ways you could place something. A fully associative cache only has one set. Everything's in the same set. And you have many ways, okay? And the way this breaks down from for the address bit, you have the tag field, the index field, the block offset. As you add more ways, if you keep the cache size the same, as you add more ways, you reduce the number of sets you have, right? Because you have more ways, that means more places within one set, so you need fewer sets to hold the same number of lines, right? So you kind of do this. As you add more ways, the index shrinks. Or conversely, as you add less ways, as you move towards a direct map cache, you need more index bits, right? So think of a 2D array of cache lines. One dimension is sets, the other dimension is ways, right? If I have a constant number of lines, if I'm increasing ways, I'm decreasing sets. If I'm increasing sets, I'm decreasing ways, right? That's the design space of these caches. Oh, one thing you might encounter, IBM likes to call things by names IBM only uses. And in particular, in cache terminology, IBM calls sets ways and ways sets. And they're just wrong, right? They're just wrong. So if you see anybody from IBM telling you you're wrong, tell them, no, you're wrong. And, I've got no idea why they started doing that, and it's persisted at IBM. And what's funny is they'll call their cache a four-way set associative cache to match what other people say. Then in the detailed description, they'll flip it around. And they're just wrong. And I don't know why, but they're just wrong. So don't get confused by IBM. So the index field is what selects the set, and within the set, there are multiple ways. Okay, now that you're thoroughly confused, let's ask you a clicker question. So just to explain this question a little. So this is a cache that has a constant total capacity, right? And what we're doing is, if we increase the number of ways by a factor of 2, which statement is false? And there are many different ways you can change the cache around. Remember, the cache has to have a constant total capacity. Which statement is false? A lot of these are could-offs rather than did, right? So, give you a couple minutes to think about this. Okay, so, a lot of confusion. So, I think I'll give you another couple of minutes to chat to your neighbors so you can convince each other about the right answer. Okay, give you another 15 seconds. Get your votes in. Okay, so not unanimous, but there's a clear winner there. Let's go through the options. I think this might be worth spending a bit of time on. So the cache is a total capacity. Now, from some of these, you could see some of the options. When you change the number of ways, all the other variables are free. I can change the block size, right, as well as... So if I look at the first answer, the number of sets could be doubled. How could you do that? I've increased the number of ways by a factor of 2. How am I going to increase the number of sets? What would be one way of doing that? Constant capacity. I double the number of ways, so there's more entries in each set. How can I also increase the number of sets while keeping the capacity the same? Yep. Right, you decrease the block size. If I divide every line in how much? 4, right? So if I cut each line into 4 pieces, I then have enough lines that I could use half of them to double the number of ways in each set, and the other half to increase the number of sets, right? So if I just quarter the line size, that would give me one way of doing that. So it's possible the number of sets could be doubled by doing that. Second one is the tag width could decrease. So at first, if you look at the previous slide, you'd say, well, wait a minute, this was a popular option. How can that happen? If I'm increasing the number of ways, that would tend to suggest I have fewer index bits, and therefore the tag must grow. How could it possibly shrink? Well, we just gave that example. If I reduce the line size, I could have more sets. If I had more sets, I would need less tag bits. So I could, that would be a free variable. I can change the line size as well. So B is actually the same answer as A, for the same reason, right? I could reduce the line size. So that's okay. C, the number of tags could stay the same. So remember, the tag is per line. So this is kind of easy. If there's one tag per line, I'm increasing the number of ways. I'm just changing whether lines are in ways or sets. I'm not changing the relationship of tags and data. So this one's obvious that the number of tags can stay the same. So the number of tag entries is always the same as the number of lines in your cache, right? There's one tag per line. D, the block size could be halved. We just talked about taking it down by a factor of 4. Sure, we can make it half as big. That's also a possibility. So the last option is the false one. The tag width must increase. It doesn't have to increase. We just talked about how it could decrease, right? So it's not necessarily true. So there are lots of interrelated parameters in cache design. And so, in the problem sets and in the homeworks and the exams, you get to explore that design space, right, of all the ways in which you can change these parameters around. And so computer architects actually spend a lot of time optimizing cache organizations because it does have quite an impact. So, for example, when you halve the block size, one of the consequences is you'll double the number of tags because each block needs its own unique tag. So sometimes you go the other way, increase the block size, because then you'll need fewer tags, and that's less hardware, right? It makes it cheaper. Okay, so these days, if you look at a typical memory hierarchy, you'll have a data path, a processor on there. You'll have an instruction cache and a data cache that are separated. So the reason you separate them is to get high performance. I can do an instruction access at the same time I do a data access. And in the simple RISC pipeline we showed you, we already assumed that was true. So that instruction memory and data memory is really the innermost level of the cache hierarchy with a separate instruction cache and a separate data cache at those stages in the pipeline. Past that point, on almost all systems, not all, but almost all systems, the caches are unified, so they hold both instructions and data. So there'll be a second level cache. And then these days it's common to have a third level cache on chip. And as we mentioned with that mainframe announcement, sometimes there's even a fourth level cache. And then finally you have main memory, then way back here you have secondary memory, disk or flash. Now notice the reason we have these levels of cache hierarchy is that the same principle applies recursively. If I have I can make a big cheap memory look fast by putting a smaller, faster memory in front of it. I can make that small, fast memory look even faster by putting an even smaller and even faster memory in front of it, right? And so I do this recursively, And so the typical sizes here, or speeds in sort of cycles at sort of gigahertz rates. Register file is in some ways the innermost part of the memory hierarchy. You can access that in half a clock cycle. The instruction cache, data cache, sort of in one cycle, the innermost caches. Second level cache is usually 10 to 20 kind of clock cycles. The third level cache on chip is more like tens of clock cycles, 20, 30, 40 clock cycles. Main memory is more like a few hundred clock cycles, 100, 200, 300, 400 clock cycles. And then disk is just, rotating disks are just off in millions of cycles away. Flash is a bit better, but still quite slow compared to DRAM. And so the goal is, with this memory hierarchy, you kind of want to make the programmer feel like they have terabytes of memory that is at nanosecond scale, right? That's the goal, that most of your accesses handle at this level, and so you feel like you can touch any part of your whole disk storage, and it'll happen in a few nanoseconds, right? Yep. That's a good point. The comment here was, well, doesn't that mean you're repeating the data in every level? So if I have something on disk and I copy it into memory, then when I access it, I'm going to copy into my third level cache. Then my access, I'm going to copy into my second level cache. I access, I'm going to copy into my data cache. Then I finally copy into my register file. So that same data item is represented in my hierarchy multiple times. So that's true. But why isn't that a big problem?
The speed at which you can write stuff closer to the processor is going to be negligible compared to going back and accessing.
Well, it's true that closer things you can access quickly, but just in terms of capacity, you have all these copies around. Why doesn't it matter in terms of how much storage I have on my machine that I have all these copies? What can you say about one of the inner levels versus one of the outer levels? What's the big difference between inner level and outer level? In terms of capacity. Right? Right. So if the inner levels are smaller, are the copies a big problem?
Yeah, so could you do this, so like if you copy them, could you like erase them from there, and if you change them, then just write them back?
Okay, so everybody's trying to optimize to only have one copy of this thing anywhere in the hierarchy. Why isn't it a big deal in terms of capacity?
So you don't have much memory in the smaller caches.
Right.
So when you load this information, you can lose the memory. You're still probably going to go back to it.
Right, yeah, so yeah, exactly. So if you look at the levels in the hierarchy, remember one goal is the inner ones are much smaller than the outer ones. So if there's copies in the inner ones, it's not many. You can only have a few things that have many copies because there's not much space in the inner ones. So most of your capacity is in the outer level, right? It's not really wasting much capacity in your system. The inner ones do have copies, but they're only a small fraction of all the stuff in the next level out, right? So it doesn't actually represent much wasted storage. If you just think about the total number of megabytes or gigabytes in the system, only a tiny fraction is in here. Most of the capacity is out here, right? So filling this with copies doesn't change how much stuff you can put in your machine, right? Okay. Right, so the reason we do this is not just because of speed, it's also because of cost. And so the big memories out here tend to be very cheap compared to the inner memory. So particularly buying disk storage, a disk you can buy, a terabyte disk for like $100 or less, probably $50 now. That's for a terabyte of disk, whereas this on-chip memory in the processor costs you a lot more than that, several orders of magnitude more per bit. So there's also a cost reason to use these memory hierarchies. Okay, so we talked a lot about caches. So far, we haven't really talked about what happens on a store when you try and write to memory. Right? We focused on what happens when you read from memory. So let's take a look at what happens with stores. It's a little more complicated. So we'll talk about one design, which we call a write-through cache. And the idea is pretty simple, that when I do a store from the processor, I get an address, and I get the data value I want to store to memory. What the cache is going to do is, if it gets a hit in the cache, it will update the version in the cache with the data you're writing, but it will also write through the cache and send that to main memory. So both the cache and the main memory are written with the data. Okay. Now the one problem here is, well, wasn't memory slow? Well, wasn't the whole point of having the cache to speed things up? If you have to wait to write stuff to memory, that's going to slow you down. So what's the point of having a cache if you're going to wait for that write to main memory? That's true. So what systems that have write-through also usually have is a write buffer, which is a little queue of entries going to main memory. So you write to the cache, and you enqueue the write to main memory in the buffer, and sometime later in the background, that will be written to the main memory. So the processor doesn't have to wait for that to complete. So this is kind of the picture here. So my address comes in, my data comes in. If it's a write, I check in here. If I get a hit, I update the cache entry. Whether or not I get a hit, I send the address and the data into the write buffer, and sometime later in the background, this will be written out to main memory. As memory is available, it may take a little bit of time for that to complete, because that happen in parallel. So it stops the CPU from stalling while waiting to complete that write to main memory. And what you realize is programs don't generally just write to memory. They do other things. While they're doing other instructions, the writes can happen in the background. And often the write buffer has multiple entries, so it can capture a whole string of things and buffer them up before going out to main memory. So the nice thing about write-through cache is when you get a miss in the cache, what do you have to do? On a write, you got a miss in the cache. I tried to write a memory location, but it missed. What do I need to do if I have a write-through structure? Nothing. Nothing. Because basically, it's not in the cache. I'm already writing it out to memory. I can just, if I get a miss, that doesn't matter. The CPU is not waiting for a value. It's just trying to write to memory. So as long as it's in the write buffer, I don't have to do anything else. Right? So I just keep going. Now, one problem with this write-through cache, it is a simpler design, but it doesn't really filter out all this traffic to memory. So your memory has to keep up. The outer memory has to keep up with all these writes going out to main memory. Right? And that can be hard. And so a different cache organization is called a write-back cache. So the idea in a write-back cache is I'm not going to write to memory immediately when I get a write. If I get a cache hit, I'll just write to the cache. And only when I kick that item out of the cache will I finally update main memory. So you only write to the cache, and you don't write to main memory. But when the cache block is evicted, when something new comes in, then I write the updated value. Only then do I write the value back to main memory. Right? So what's nice here, if I repeatedly write the same location, all those writes will just happen in the cache. They'll just update the cache. Memory won't see them. Only finally, when that block is evicted for some reason, will I actually send the final version to main memory. Now, one optimization that's made here in write-back caches is the addition of what's called a dirty bit. So already mentioned this valid bit on every cache line that just indicates the line had valid data in. The dirty bit is a second bit that you use in the write-back cache, and this differentiates between, did I write to this line while it was in the cache, or is it clean? So when you first read a line, it comes into the cache clean, which means it's the same as the version in memory, right? So the version in memory and the version in the cache, they're the same. In a write-back cache, if I then store to that cache line, I change the value in the cache, and it's now different from the value in main memory. And so when I do a store to the cache, I update this bit to say it's dirty. Now later on, when that cache line is evicted, I check the dirty bit. And if it's clean, I don't need to do anything. I just overwrite that location with the new data. It's only if that line is actually dirty do I actually have to send the data to memory and update memory. And then it will be up to date with the newest version, right? So in the write-back cache, you have the tags and the data. So when you do a write into the cache, if you get a hit, you write to the cache and set the dirty bit. And at that point, memory will have a stale value. On a miss, so in the write-back cache, when you get a miss, you actually have to bring the old data in from memory and then overwrite it. Right? So you bring it in clean and overwrite it immediately when you get a write miss. And it's only when the cache is evicted that you kick it out. Yeah, so loads will just use the value from the cache. And on any miss, the victim line that you send back out, if it's dirty, you write it back. Otherwise, you don't have to do anything. Okay, so to compare these two, so write through is simpler logic. It's more predictable because when you make an access to the write through cache, it always does the same thing regardless of whether there's a cache hit or not. Just enqueues things to the right buffer. It's also easier to make it reliable, which is one reason people use it. Because notice there's always a copy of the data, even in the cache and main memory. So the cache isn't the only version of the data. This big idea of redundancy. The write-back cache is more complex. And also it can do 0, 1, or 2 memory accesses per cache. It's a little bit more complicated to control. But it does cut down that write traffic. But the downside is hard to make reliable. Okay. So, yeah, we talked about locality. We talked about hierarchy, caches, direct mapped. Next few lectures do some more cache design studies. Okay.